67. Find all the zeros and their multiplicities of the function. Begin by finding the possible rational zeros and comparing the possible values with the graph of the function on the calculator. Check the values using division, usually synthetic, show all work. All right, so we're going to start off by finding factors of 2 and 20. So factors of 2 are 1 and 2. Factors of 20 are 1, 2, 4, 5, 10, and 20. So possible roots are plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 5, plus or minus 10, plus or minus 20, plus or minus, now we start getting, technically these were all divided by the 1, but now we're going to divide by 2 through everything and make sure that we don't repeat. So plus or minus 1/2. 2 divided by 2 is 1. We already have that. 4 divided by 2 is 2. We already have that. But we don't have 5 divided by 2. 10 divided by 2 is 5. And 20 divided by 2 is 5. So here are all our possible rational roots. So if we graph the function, we can see by inspection we see a bounce at x equals 1. And it goes through, that looks like about -5/2, somewhere between that like 2 and 3 in the negative side there. So now we can start doing synthetic division or polynomial division. Might as well do synthetic division. So we get 2, 1, there's no cube, so we have to remember that 0, 9, 32, 20, and since we said we go through 1, that'd be a nice easy one to check. So 2, 2. So 2, 3, 3, 3, 3, 12, 12, -20, -20, 0. So yes, 1 is a root, but we said it kind of bounced, so that implies that there's probably more than 1 there. So now we'll do this again. So 2, 2, 5, 5, 8, 8, 20, 20. Look at that, we still get a 0 yet again. So now we can check that -5/2. 2, 5, 8, 20. So 2 times -5 is -5, 0. 0 times that is 0. We get 8. 8 times -5, it would be -40, divided by 2 is -20. So we get a 0 yet again. At this point, we can write this as 2x squared plus 8. And we can just directly solve for our remaining zeros. So we find that they actually are imaginary. So does it ask for, no, just the zeros here. So zeros, 1, 1, negative 5 halves, 2i minus 2i. So in terms of multiplicities, it would be 1 multiplicity 2, negative 5 halves multiplicity 1, 2i multiplicity 1, and negative 2i multiplicity 1. Write a polynomial of degree 3 in standard form with integer coefficients of 3i and 4/5. Show all work. So they gave us 2, but since one of them was imaginary, they gave us all 3 roots. So we're going to set that up as, we'll just call it f of x is equal to x plus 3i, x minus 3i, and x minus 4/5. We'll do the x, or the imaginary parts first. Be x squared plus 3ix minus 3ix minus 3i 9i squared, x minus 4/5. F of x is equal to, once we simplify, x squared plus 9 x minus 4/5. So now we can multiply through here. So we're going to get x cubed plus 9x minus 4/5 x squared minus 36 over 5. Rewrite that in standard form. Now it did ask for integer coefficients, so we're just going to have to multiply everything through by 5. This does not affect the zeros in any way. So even though I said we've been doing f of x is equal to, I'm going to switch the notation just so I'm mathematically consistent, but I'm going to multiply everything through by 5. So 5x cubed minus 4x squared plus 45x minus 36. Write a polynomial of degree 4 with integer coefficients given that some of the zeros are negative 2, 5, and 2 plus 3i. Show all work. So again, they've given us a imaginary root, so we automatically know that we already have 4 roots. So we'll write these out. x minus 2 plus 3i and x minus 2 minus 3i. Okay, and where we have 4, we can kind of do a few things at the same time. So I'm going to multiply these two together, which will be x squared minus 5x plus 2x minus 10, and then we're going to multiply these two together. So we're going to get x squared minus 2 minus 3i in parentheses x minus 2 plus 3i x plus 2 plus 3i multiplied by 2 minus 3i. Then we can do some simplification on that first multiplication. So we can get x squared minus 3x minus 10. Over here we'll get x squared. We might as well distribute some of those. So minus 2x plus 3ix minus 2x plus 3ix, and then here we'll multiply all those out, so we'll get 4 minus 6i plus 6i minus 9i squared. Then we'll do some simplification. Over there, we'll leave this guy alone. There's not a whole lot we can do right now with him. Oh, this should have been. That'll be a minus 3i. So that will cancel with this. That cancels with this. And then we can combine the minus 2x plus 4 plus 9 okay. Now we can do all the multiplication here. All right, so we'll multiply this by those 3, so we'll get x to the 4th minus 4x cubed plus 13x squared. Now we'll do this one. Minus 3x cubed plus 12x squared minus 39x. That'll be a plus. Right? No, minus. Okay. And now last, this minus 10. So minus 10x squared plus 40x minus 130. Now we can start combining everything. So we'll get f of x is equal to x to the 4th. Start with minus 4, minus 3, so we're at negative 7. So minus 7x cubed, so plus 13x squared, plus 12, so we're at 25x squared, minus 10x squared. That will give us 15x squared. Then, let's see, going through minus 39x plus 40x, so plus x minus 130. Given the function f of x is equal to x plus 2 over x squared plus 6x plus 8, write the domain in interval notation. So we look at things that might restrict the domain. The top doesn't have anything that would restrict the domain. The bottom will, just because we'll have some value divided by 0. So we need to find the zeros of that bottom. So we have x squared plus 6x plus 8, which is easily factored, and we're trying to see when these are equal to 0. So x equals 0 at -4 and -2. So those two values are outside the domain of the f of x function. So the domain will be from -infinity to -4 union -4 to -2 union -2 to positive infinity. Find the vertical asymptotes of the following functions. 3 over x squared minus 3x minus 18. So vertical asymptotes are going to occur when the denominator is equal to 0. So if we set the denominator equal to 0, 3x minus 18 equals 0, we can factor that. So x minus 6, x plus 3 is equal to 0. So x is equal to -3 and 6. So there's vertical asymptotes at those 2 points. B, x minus 5 over x squared plus 16. So if we try and attempt that same thing, x squared plus 16 is equal to 0, and we try and solve. Get x squared is equal to -16, x is equal to plus or minus 4i. Since this is a non-real value, there are no vertical asymptotes. So C, x plus 2 over x squared minus x minus 6. So this one, we're going to have to be careful and check to make sure that the numerator and the denominator don't have similar factors. So after simplifying, we see that it's x minus 3. So since it's only asking about vertical asymptotes, it'll only have a vertical asymptote when x minus 3 is equal to 0 or at x equals 3. It'll still be undefined at x plus 2, but it only has a vertical asymptote at x equals 3. Okay, horizontal asymptotes for question 72. We are going to compare the leading coefficients after we have compared the powers. So this one has x to the third, and the highest power here in the denominator is x squared. So there is no horizontal. B, 2 over x squared minus 3x plus 5. This is implied x to the 0 here. So our denominator's power is greater, so the horizontal asymptote occurs at y equals 0. Part C, you have 2x squared minus 5x plus 3 over 3x squared plus 2x. So the power, or the highest power in both of them are equal. So now we look at their coefficients, and that's where the horizontal asymptote will occur. So horizontal at y equals 2/3. 73. For the following functions, determine if a slant asymptote exists. If a slant asymptote does exist, find the slant asymptote and show it'll work. So a slant asymptote is going to be a linear function in the remainder. So it would be something like 3x plus 5 over whatever we're dividing by, x squared minus 5. So because of that, if this is to be linear, our numerator needs to be 1 power higher than our denominator. So in the case of A, we have an x cubed as the highest power, and the highest power of the denominator is just x to the first. So there is no slant asymptote in function A. Part B, similar thing, we're going to look at the power of the numerator, which is 3, and the power of the denominator, which is 2. So there's a potential slant asymptote here. We're going to have to divide it out to see if one exists. So x squared minus 5 divided by, oh no, we'll just lower that. Okay, start this lower. X squared minus 5 divided by, or 2x cubed plus 3x squared minus 5x plus 2 divided by x squared. So to get to x cubed, we need to be 2x. So that'd be 2x cubed minus 10x. Subtract that off. So we'd be left with 3x squared plus 5x plus 2 plus 3x squared minus 15 would be 0 plus 5x plus 17. So since there's a remainder there, that will become our slant asymptote, the 2x plus 3. All right, 74. Find the nonlinear asymptotes for the following functions. Show all work. So unlike slant asymptotes that just have to be linear, they don't have to be linear anymore. So we'll use polynomial division. 2x to the 4th plus 8x squared plus 10x minus 8. Okay, now we ask, what do we need to get to negative 2x to the 4th? It would be negative 2x squared, so minus 2x to the 4th plus 2x cubed minus 4x squared. And we're going to subtract that off. So 0 minus 2x cubed plus 12x squared plus 10x minus 8. Now we're going to say, what do we need to get negative 2x cubed? be negative 2x. So negative 2x cubed plus 2x squared minus 4x, and then we'll subtract that off. 0, 10x squared plus 14x minus 8, and then plus 10, 10x squared minus 10x plus 20, subtract that off, be left with 0, 24x minus 28. At this point we can't do anything, but that's going to be our non-linear asymptote. B, same idea here. Okay, same idea. What do we need to get here? 2x squared. So 2x squared plus 8x squared. We'll subtract that so we get 0. Negative 3x cubed minus 9x squared plus 10x minus 5. What to get to there? Minus 3x. So minus 3x cubed minus 12x. Subtract that off. 0. Minus 9x squared plus 22x minus 5. What do we need to get to there? Or to negative 9x squared, negative 9. Negative 9x squared minus 36. Subtract that off. 0 plus 22x plus 31. At this point, we can't divide any further, so that is our nonlinear asymptote. Find the x and y intercepts of the following functions. All right. So the y-intercept is found whenever x equals 0. So for this first one, we'll say 0 plus 3 times 0 minus 5 over 0 plus 4, 0 minus 3, which is going to equal negative 15 over negative 12, which will give us simplified 5/4, or you could say the intercept in the coordinate form. Okay, the x-intercept is whenever the y equals 0, so we can set 0 equal to x plus 3, x minus 5 over x plus 4, x minus 3. So as long as the zeros on the top do not make the zeros in the denominator, or make the denominator 0, we only need to find when this equals 0. So 0 is equal to x plus 3, x minus 5, or x is equal to negative 3 and positive 5. And if we look, that doesn't make the denominator 0. So the x-intercepts are going to be at negative 3, 0, and 5, 0. Part B, g of x is equal to x plus 2 over x squared minus x plus 3. So the x-intercept is when our x equals 0. So the y-intercept is when x equals 0. So 0 plus 2 over 0 squared minus 0 plus 3 is equal to 2/3. Or 0, 2/3 is the y-intercept. The x-intercepts are when y equals 0. The x-intercepts are where y equals 0. So again, as long as the value in the top doesn't make the value in the bottom 0, we're good. So 0 is equal to x plus 2, x is equal to -2, but let's check and make sure that that doesn't zero anything out. So that would be -2 squared minus -2 plus 3, which will be 4 plus 2 plus 3, which is 9. So that does not make the function undefined. So the x-intercept is at -2, 0. Determine if any point, or determine the point, if any, where the graph of the function crosses the horizontal asymptote of the function. F of x is equal to -4x squared plus 5x minus 1 over x squared plus 2. Show all work. Okay, so first thing to notice is that we have the same power, so it'd be -4 over 1, or -4 is the horizontal asymptote. So then we will set the function equal to -4 and see if there's a solution for x. So -4 is equal to -4x squared plus 5x minus 1 over x squared plus 2. Going to multiply both sides by x squared plus 2. Which will be -x squared minus 8 is equal to -4x squared plus 5x minus 1. Should get everything onto one side here. So we'll add 4x squared so we get 0 is equal to 5x plus 7. Now we can solve for x. Being -7 divided by 5 is equal to x. And that is the only place that it crosses the x, or the horizontal asymptote. So the ordered pair would be -7/5, comma, -4. All right, last but not least, 77. Graph the rational function f of x is equal to x squared minus 2x divided by x squared minus 3x minus 18. Okay. To help us out, we're going to start filling out the charts below. So we're going to determine the domain of this function. So the domain is not, everything on top is okay. There might be values on bottom, particularly whenever that equals 0. Minus 3x minus 18 is equal to 0. That factors to x minus 6, x plus 3. So at x equals -3, and positive 6, it is outside the domain. So the domain will be negative infinity to negative 3, union negative 3 to 6, union 6 on to positive infinity. It then asks for the y-intercepts. The y-intercept is when x is equal to 0. So we'll kind of block this off. 2 times 0 squared minus 2 times 0 all over 0 squared minus 3 times 0 minus 18. Some of you might be already screaming at me going, Matt, don't you understand that the 0 or that the top is already 0? So it happens at 0, or the ordered pair will be 0, 0. X-intercept, that is where the function equals 0. So 0 is equal to 2x squared minus 2x over our x squared minus 3x minus 18. Since we already found our domain, as long as our top doesn't give us back negative 3 or positive 6, we can find x-intercepts. So so this will be 0, or we can just set the top equal to that. 0 is equal to 2x, x minus 1, so x equals 0 and 1. So those intercepts will occur at 0, 0 and 1, 0. It asks for vertical asymptotes, which we would have already found with our domain, but we'll express them as x equals negative 3 and x equals 6. Horizontal asymptote. We've not found that, but if we compare the order to the top and bottom, we have x squared to x squared. So then it would be 2 divided by 1 is equal to 2, or at y equals 2. So then it now wants to know if it crosses the horizontal asymptote. So we would set 2 is equal to 2x squared minus 2x all over x squared minus 3x minus 18. Multiply the denominator over, so we get 2x squared minus 6x minus 18 times 2 is equal to 2x squared minus 2x. So that's going to cancel with that. We're going to get negative 32 is equal to 4x. That'll be negative 36, my apologies. And then we'll get negative 9 is equal to x, or the ordered pair will be negative 9, 2. So that occurs at negative 9, 2. Slant asymptote. So the numerator would have to be 1 degree higher than the denominator. Since they are equal, there is none. So now we can start putting in some of our constraints here. So we'll have a vertical asymptote at -3 and at 6. We then have a horizontal asymptote at 2. We have a y-intercept at 0, 0, and an x-intercept at 1, 0, also at 0, 0. Now we should probably test some points in the different areas to see what the shape of the graph will look like. In addition to that, we can also graph it on a graphing calculator and see what the shape will be. But this will help us get a better idea of where to put our lines. So we can pick a few points, and there's been some that have been calculated off camera here, but I'll write them down here. Okay, then we can plot some of these points here. So 9, 4, 7, 8.4, 3, and -0.67, so not quite to -1 there. At -2, we're at -1.5. At -4, we're at 4. At -6, we're at 2.33, and at -8, just above 2. So this should be enough information to say, oh, and also at -9, we're at 2. So this will be enough information to say, to actually draw our lines here. And then goes like this, dips above, and then kind of comes back down, curls over like that. And there we go.